Hi, my name is Max Pan, and I'm a rising junior at UC Berkeley. I first want to give thanks to my advisor, Professor Shelton, for his mentorship and wisdom throughout the summer. And my research project has been the bulk band structure calculation of bismuth-2, tellurium-2, selenium. So this material belongs to a family of compounds known as tetradiamides, which consists of a group 5 metal and a group 6 anion. These compounds also possess rhombohedral symmetry, and they are formed by stacks of quintuple layers that are connected via van der Waals interactions, which are intermolecular bonds that are electrically induced. As you can see to the right, bismuth-2 tellurium-2 selenium is derived from the parent compound bismuth telluride by replacing the middle tellurium layer with a layer of selenium. So why are we interested in these materials? Well, bismuth-2 tellurium-2 selenium has been experimentally determined to be a topological insulator, in which topological insulators are materials that are insulating at the bulk and conducting at the surface. They can have applications such as non-volatile RAM due to a special property called spin momentum locking, in which the spin of the electron is normal to the momentum of it, which can be seen in the picture to the right. The arrows represent the spin of the electron. Another important aspect of research of topological insulators is that we currently have difficulty observing the surface transport. So what band structure is the plotting of energies of molecular orbitals in regions of space. Atomic orbitals are characterized as having discrete energy levels and are degenerate as well. However, when they bond with other atoms to form molecules, these degeneracies get lifted and give rise to a complex band structure, which can be used to determine certain physical properties. So for the band structure, the valence bands are the bands such that they are completely filled, and the conduction bands are the bands that are empty. And the Fermi energy, which is usually set to 0 of the plot, is what separates these two bands. At the bulk of the topological insulator, a process called band inversion occurs, in which the conduction band and the valence band, there's a sort of crossing over process, in which results in an inverted curvature, which is known as the Camelback feature. The surface band structure of topological insulators are characterized as having these linear gapless states, which form this double cone shape known as the Dirac cone. And the Dirac point is the apex of this cone. So for the observation of surface transport, for surface band structure, the requirement is that the Dirac point has to be at the Fermi energy level, and that the bulk must be electrically insulating. One material in which the Dirac point is at the Fermi energy level for the surface band structure is bismuth selenide. In addition, there is another interesting feature of this material. As you can see here in the circled region, there's a almost linear, almost Dirac cone-like shape, but instead it has a gap in it. It is also important to note that it is centered around the Fermi energy level. This is known as the Dirac feature. Now, from the bulk band structure to the surface band structure, it almost appears as if these bands are moving towards each other to form a Dirac point at the Fermi energy level. However, for bismuth selenide, it is chemically unstable, which makes it very difficult to obtain an electrically insulating bulk. On the other hand, bismuth-2 tellurium-2 selenium is determined to be more chemically stable, and since it is in the same family of compounds as bismuth selenide, the same feature might occur. So based on past experimental data of angle result photoemission spectroscopy, the location of the Dirac point for bismuth-2 tellurium-2 selenium seems to vary a great amount. This can be seen in the left of these two samples, in which the Fermi energy is indicated by the white line. For the native 1 sample, the Dirac point is approximately 0.1 electron volts away from the Fermi energy level, while for the native 2 sample, the Dirac point is approximately 0.3 electron volts away from the Fermi energy level. So because of this, it is now important to rely on the theoretical calculations. So the method for this involves the use of a software called the Vienna AB Initio Simulation Package, or VASP as an abbreviation, which makes use of the density functional theory, which is based on the fact that ground state energy can be expressed as a functional of electron density. It is also iterative, which looks for the convergence of the density functional and the ground state energy. Another process that is utilized is ionic relaxation, which optimizes the atom positions and lattice parameters. Furthermore, the plane wave pseudopotential approach is used, in which the solution is a linear combination of plane waves, and the core electrons are not included in this basis and instead are represented by an effective potential. So one aspect I believe that made my calculations accurate was the inclusion of van der Waals interactions. Density functional theory traditionally does not take into account van der Waals interactions, and as a result, lattice parameters are often overestimated. So two sets of calculations were done, one without the corrections and one with the corrections. With respect to the experimental values, the lattice parameters without the corrections overestimate by approximately 2%, while with the corrections, there is approximately a 0.5% error. And this has a significant impact, as the change in the Fermi energy is approximately 1 electron volt, and the change in the ground state energy is approximately 6 electron volts. So here is a band structure that I have calculated. As you can see in the red circled region, there is a Dirac feature mentioned as before. However, instead of being centered at the Fermi energy level, it is centered 0.4 electron volts below the Fermi energy, in which, as an estimate, which indicates that the Dirac point of the surface band structure might be 0.4 electron volts away below the Fermi energy level, which makes it unsuitable, which most likely makes it unsuitable for the observation of surface transport. So just to recap, I have done the bulk band structure calculations for bismuth-2, tellurium-2, selenium. The accuracy of these calculations can be supported by the resemblance of the optimized lattice parameters with the experimental values. And due to how far the Dirac feature is from the Fermi energy level, bismuth-2, tellurium-2, selenium might not be adequate material for the observation of surface transport. And in addition, the accuracy of these calculations can give a strong foundation to valid surface band structure calculations. So in the future, I will calculate the surface band structure. In addition, other compounds that might be suitable for, that might be topological insulators and also suitable for the observation of surface transport are BSTS compounds. And this is based on the fact that antimony telluride has a Dirac point that is significantly above the Fermi energy level, which can be seen in the left picture. In addition, some BSTS compounds have been known to be chemically stable. I would like to thank the NSF-REU, as without the financial support of the NSF-REU, I would not have this opportunity to do summer research. And a special thanks to Professor Moreno. And thank you for your attention.
You are welcome, Max. Questions? I have a question. What plan do you have now to the doping? You want to explore different dopings of the selenium. Do you have a plan of how to do that?
That's not actually in my agenda. It's just that these compounds are, belonging to tetradiamides, and as well, it's more that it's not like in my specific agenda.
Okay. Any other question or comment? Okay, if there is no any other question, let's thank Max and everybody that have talked today.
Very nice, everybody.